I welcome everyone to the Journal Club meeting of Nano Energy and Catalyst Research Lab from Ajou University.
Hi, this is Dr. Jansi Rani, postdoctoral researcher from Nano Energy and Catalyst Research Lab. Today I am going to present my work entitled Synthesis of Faceted CuMn2O4 nanopolyhedra with enhanced electrocatalytic HER activity for water splitting. Introduction to electrocatalytic, that is easy water splitting. First of all, we should know the importance of easy water splitting. In recent years, energy consumption is tremendously increasing, which leads to a very big challenge for sustainable energy all over the world. Electrocatalytic water splitting approach is one of the promising approaches to produce clean energy hydrogen with zero carbon emission. We all know that. Since hydrogen evolution reaction, that is HER, and oxygen evolution reaction, that is OER, is consisted by the electrocatalytic water splitting. The conventional electrocatalyst and the requisite of new electrocatalyst for easy water splitting are conventionally platinum and ruthenium iridium based materials are used for easy water splitting. Generally platinum is used for HER, ruthenium and iridium based oxides are used for OER activity. But the scarcity and poor stability of such precious metal catalyst limits their advantages to the large scale. So we have to develop a new highly active, robust and cost-effective electrocatalyst for easy water splitting is still a milestone in the energy related research area. In such a way, spinel oxide catalyst, that is SOCs, are one of the most important and efficient electrocatalyst to use for electrocatalytic water splitting. In such a way, ternary spinel oxide catalyst, that is Ab2O4 structure electrocatalyst, where A stands for tetrahedral site and B stands for octahedral site. Those are having intrinsic catalytic activity compared to other noble metal based electrocatalysts. Still, the poor conductivity and restricted active sites are the major concerns we need to address to use these SOCs as an efficient electrocatalyst for water splitting. Interestingly, SOCs are exhibited remarkable HER and OER activity depends on their morphology and particle size. So, synthesis of active sites rich morphology controlled SOCs would draw the wide range of attention to produce a new electrocatalyst for water splitting. Spinel manganese oxide catalyst. Among the other SOCs, specifically the spinel manganese oxide catalyst, that is Xmn2O4, where X could be cobalt, nickel, zinc, copper, anything it may be. The spinel manganese oxide electrocatalysts are performing well for potential applications due to their unique electron transport ability in various oxidation states, high electrical conductivity, more active sites, and good stability. Still, one of the cheapest spinel manganese oxide electrocatalysts in the first 3D transition metal family, CuMn2O4, that is CMO, is not explored as a bifunctional catalyst for electrocatalytic water splitting application. Also, the detailed exploration of active facets, electronic conductivity and electrocatalytic mechanism of CMO still remains unknown. Therefore, in this work, we are focusing to synthesize the faceted CuMn2O4 nanopolyhedra via ethylene glycol, that is EG assisted hydrothermal HT method. Initially, we took copper chloride and manganese chloride as precursor materials in 1:2 ratio. And then these two are mixed together in the solution of EG and DI water, where 50% of EG and 50% of DI water is in the solution. Now the color of the solution is pale blue, and then 5 mole of NaOH has been added to the solution to fix the pH as 11. At pH 11, the color of the solution is completely different, which is brick brown color. And then the solution has been transferred to a Teflon lined autoclave to treat at 160 degrees Celsius for 12 hours. After naturally cool down, the solution has been taken, the suspension has been taken from the hot air oven, and then this suspension was cleaned by using DI water and ethanol few times, and then the final precipitation has been dried overnight. After that, the powder has been annealed at 3 different temperatures as 400, 600 and 800 degrees Celsius. Here, the particle growth mechanism of CMO, that is Cu and Mn3O4. After taking from the hydrothermal treatment, the powder is the mixture of Cu and Mn3O4. We have confirmed it via XRD. I will discuss it later. So here the particle growth mechanism. Ethylene glycol played an important role as a reducing agent to produce copper, and via Oswald ripening process, Mn3O4 nanopolyhedra has been formed. Then during the annealing, post-annealing process, these two, that is copper and Mn3O4, are undergone the solid state reaction finally to produce CuMn2O4 nanopolyhedra. And then CMO electrode preparation. Here we have adapted the planetary ball milling method to produce high quality ink. In this process, 2 gram of our CMO, 10 ml of ethyl alcohol and 2% of KD6 dispersant are mixed together, and then which was subjected to planetary ball milling process for 50 hours to produce the high quality CMO ink. And then this ink was drop casted on the cleaned copper foam to produce the copper film coated CU electrode, that is CMO electrode coated on the copper foam, shown like this. Results and discussion. Structural conformation of faceted CMO. Here I have seen the XRD before and after annealing. Before annealing, we could clearly see that the formation mixture of copper and Mn3O4, and then after annealing, these two are undergone the solid state reaction to produce CMO. Here we can see that the pure phase CMO has been obtained from our EG assisted HT method, and then the crystallinity of the CMO is increasing with respect to the increase of post annealing temperature as 400, 600 and 800 degrees Celsius. The cubic crystal structure of the CMO has been obtained from this method, and which is shown in the crystal structure diagram. Morphological analysis of faceted CMO. Here I have shown the semi-image of CMO before and after annealing. Before annealing, we could clearly see that there is some aggregation and very small particles formed, and we cannot see the clear faceted morphology here due to the agglomeration. And some after annealing shows the clear faceted morphology. Here I have to mention that the CMO produced from 400, 600 and 800 degrees Celsius post annealing was named as CMO 400, CMO 600 and CMO 800 respectively. Here we can see that CMO 400 shows so much of aggregation with very small particles. CMO 600 shows some facets. CMO 800 shows the clear faceted morphology due to the bigger particles. And then EDS mapping and EDS spectra from the semi-images. Here we can see that the uniform distribution of elements like copper, manganese and oxygen in CMO 400, 600 and 800 respectively. Here we could also confirm that the atomic percentage of copper, manganese and oxygen as 1:2:4, which further confirms the spinel formation of CMO. Surface analysis of CMO electrodes. Here we have taken some images for the CMO electrodes, that is CMO 400, 600 and 800 electrodes. So among these 3 electrodes, CMO 600 shows the conformal coating on the copper foam substrate, which is due to the optimal particle size and very less aggregation. particle size and microstructure analysis of faceted CMO. Here we have shown TEM, HR-TEM and TEM elemental mapping of our CMO nanopolyhedra. Here the particle size of CMO 400, CMO 600 and CMO 800 are 23, 48 and 155 nanometers respectively. It confirmed that the particle size of CMO has been increased with the increase of annealing temperature, and then clear faceted morphology has been confirmed via HR-TEM images of CMO, all the CMO nanopolyhedra. Here we also confirmed that the formation of cubic CMO from the despacing value obtained from HR-TM, which is coincide with the despacing value obtained from XRD. Then the good crystalline nature of all the three samples has been confirmed from SAAD pattern. Finally, the uniform elemental distribution of Cu, Mn and oxygen in CMO nanopolyhedra has been confirmed from the TEM elemental mapping. Electrocatalytic HER activity of faceted CMO for water splitting in 1 mole kWh electrolyte solution. The polarization curve shows that the HER activity of CMO 400, 600 and 800 along with the 20% PTC. Here we can see that the lower over potential of 154 millivolt at 20 milliampere per centimeter square current density is achieved by CMO 600 electrode, which is lower than CMO 400 and CMO 800 and much closer to 20% of PTC electrode. Also, CMO 600 electrode outperforms than 20% PTC electrode at high current densities. Here we also could see that there is some current density at zero potential, which might be due to the oxidation and reduction peaks of copper and manganese present in CMO, which is confirmed from the cyclic voltammogram curve. And then the corresponding Tuffle slope value of these prepared electrodes has been shown here. And the Tuffle kinetics of CMO 600 is much lower than the standard PTC electrode, which shows the favorable HER kinetics associated with the CMO 600. The better HER activity of CMO 600 might be due to the optimum particle size with less aggregation and conformal coating than other CMO electrodes. Electrochemical impedance spectra, that is the EIS spectra of CMO 400, 600 and 800 electrodes has been shown here. From this, the RCT values of 400, 600 and 800 electrodes increases with respect to the annealing temperature, which is due to the increase of crystalline nature. And then the R intermediate, that is intermediate formation resistance of CMO 600 is much lower than other two electrodes, so which supports for the higher activity of CMO 600. And then the CV curve deriving for ECSA linear plot is shown here. From the CV graph, the linear plot of ECSA has been drawn here. So from this, the CDL of CMO 600 is much higher than the other two electrodes as 43.7 millifarad per centimeter square. The chronoamperometry test, that is stability test of CMO, has been shown here for 50 hours. So we can see that the clear, obvious no decrement in the current density even after 50 hours. There is no loss here. And then the polarization curve before and after stability has been run for the CMO 600 electrode, which shows that no overpotential and the current decrement is associated with the CMO 600 electrode even after 50 hours of electrolysis. We were curious to know about the OER activity of our faceted CMO electrodes in the same 1 mole kWh solution, so that the OER polarization curve has been obtained for all the three CMO electrodes. Among these three 3 CMO electrode. CMO 600 shows the better activity as 406 millivolt over potential at 10 milliampere per centimeter square current density, but which is quite larger. So we are interested to incorporate the COOX co-catalyst on the CMO 600 electrode by dip coating method. Here, as expected, COOX at CMO 600 electrode exhibited 360 millivolt over potential at the same 10 milliampere per centimeter square current density, which is closer to the standard ruthenium oxide electrode. Then the corresponding Tuffle values of all the electrodes has been shown here. Here we could see the lower Tuffle value of 108.3 millivolt per decade has been obtained for COOX at CMO 600 electrode, which is closer to the ruthenium oxide electrode. And then the chronoamperometry test for 45 hours has been run for the COOX at CMO 600 electrode. Here we can see there is some loss, that is 40% loss is obtained for the electrode after 45 hours of electrolysis. Then the polarization curve also shows that there is some decrement in the activity after the 45 hours of continuous electrolysis. Then the ECSA and the EAS analysis of COOX coated CMO has been shown here. Here we can see that the higher CDL value of 47.4 millifarad per centimeter square is obtained for COOX at CMO 600 electrode, which is due to the more number of active sites provided by this COOX co-catalyst to CMO 600 electrode. Then the EAS analysis also shows the similar circuit, similar fitted circuit as before. So from this we can say that the COOX coated CMO 600 electrode performed well for OER activity by providing the abundant number of active sites towards the water splitting process. Here the easy activity of the controlled electrodes in 1 mole KOH solution has been shown. The HER and OER activity of the controlled electrodes shows the higher over potential values for both HER and OER than our CMO electrodes. In order to confirm the faceted morphology enhance the electrocatalytic activity, we have synthesized the CMO nanoparticles via co-precipitation method, that is without hydrothermal method. So here the XRD shows the same CMO, that is cubic CMO phase of the nanoparticles obtained, but here there are some Mn3O4 impurity without HT treatment. Then the SEM before annealing shows the similar kind of aggregated morphology. Then after annealing shows there is no polyhedra morphology of these CMO nanoparticles, which shows that not only EG but also the hydrothermal treatment influences to produce the faceted CMO nanopolyhedra morphology. Comparative easy analysis of CMO without the HT has been shown here. Here we could obviously see that the CMO 600 synthesized from the HT treatment shows the very better activity of HER and OER. And also the particle size difference is very clear from this CV graph. The inserted image shows the particle semi-image of those two nanoparticles. Here we could clearly see that the particle size also very different and morphology also different. So the particle size and morphology influences much in the electrocatalytic activity towards water splitting. X-ray photoelectron spectroscopy, that is XPS analysis of CMO samples, has been shown here. It confirms the formation of CMO and their oxidation states. Here we could clearly see that CMO 600 possessed the high number of Cu1 plus percentage and the corresponding oxygen vacancy percentage. which clears that the more number of oxygen vacancies produce the electrons. So these electrons reduce the Cu2 plus to Cu1 plus. Also, this oxygen vacancies improve and promotes the electrical conductivity of the sample, which is one of the most important reasons for the higher activity of CMO 600 compared to other CMO. We made CMO 400, CMO 600 and CMO 800 pellets to study the electrical conductivity of our samples via Hall voltage measurement. It confirms that a CMO 600 electrode possessed a very low resistivity. That means the higher electrical conductivity than other two samples. And the surface analysis of pellet also shown here. Here the smooth and uniform surface has been obtained for the CMO 600 pellet, which is due to the optimum particle size and very less aggregation. This is the comparison bar chart of electrocatalytic HAR activity of CMO with other reported spinel oxide catalysts. Here we can see that the faceted CMO 600 shows significantly low over potential compared to other spinel oxides reported in the literatures. It remarkably evidences the faceted morphology of CMO influence on the higher HAR activity. Hence, the reported low over potential of 234 millivolt versus RHE is obviously prominent, corresponds to the other spinel oxide catalysts at the same higher current density of 100 milliampere per centimeter square. Finally, the easy performance of the two electrode cell for overall water splitting. The two electrode scheme is shown here. Here the COOX at CMO 600 electrode used as anode, CMO 600 electrode used as cathode. This cell needs a cell voltage of 1.9 volt to achieve 10 milliampere per centimeter square current density, which is quite larger than the standard ruthenium and PTC cell, which requires only 1.63 volt cell voltage. The stability of the standard ruthenium and PTC cell fell almost a similar performance of our CMO 600 pair at 20 hours of water electrolysis process. Here you can clearly see from the CA test 50% of initial loss to attain the equilibrium of a cell voltage to our CMO pair. After that, a CMO 600 cell sustains for a long time even at higher potential of water electrolysis without any loss. Most of the studies are focused only on the over potential at very low current densities like 10 or 20 milliampere per centimeter square, which is insufficient for practical applications, because the typical water electrolyzer operates on the current density of 300 to 400 milliampere per centimeter square and the cell voltage between 1.7 to 2.4 volt. It strongly evidences that our CMO could be adapted for sustainable practical water splitting systems. Yeah, I hope this presentation could be helpful to you all to know about my research work towards electrocatalytic water splitting. Thank you.